Okay. This is a workshop. What? Five? This is a workshop 5 of Theory Track. Yeah, we're right here. Given that the crowd consensus is to do both differential privacy and ensembling, we will talk about both. Ensembles has no slides associated with it.
Incredible.
So I will just be yapping for a long time.
Incredible.
Okay, so this is all the content we're going to cover for privacy today. So we're going to first motivate why we need privacy. We're going to then talk about our first private mechanism, randomized response. Then we're actually formulate privacy in terms of mathematical notation, and then more math notation with differential privacy and the curator model. What's wrong with you? Then we're going to talk about Laplacian noise, which is another mechanism for privacy that is better than what we were going to talk about first, randomized response. Then we are going to talk about post-processing and privacy, because we're going to see that even if we guarantee privacy, people can do other stuff, and we need to guarantee privacy to any other function that can be applied to our output. Then we are going to talk about approximate differential privacy. So reason for that is differential privacy is very hard to achieve, so we approximate it instead. Crazy how that works. Then we're going to talk about the Gaussian mechanism, which is a form of approximate differential privacy, and that is very commonly used. Then we're going to talk about the basic and advanced composition theorem. And hopefully those terms mean nothing to you yet. And then finally, private machine learning. So bullet points 1 through 9 will actually mainly deal with something called taking the mean of the data set. And we will only preserve privacy for taking the mean of the data set. So hopefully by the time we get to 10, you will be like, wow, privacy preserving machine learning is really effing hard. That is probably the point of this. And then a bonus content for online learning and ensembles. Okay. Yeah, this is a plug for specifically Akash.
It's already filled.
It's already filled.
It's already filled.
I know. PT requested. Annoy him. I could cut this out, by the way. Annoy him. Go to his class every day. Say you're super smart and say you love theory and machine learning, and he will give you a PT.
I don't yet.
Okay.
I'm too lazy to cut this out. Wait, what class does
it cutting this out? Huh? He's on sabbatical this quarter. Usually, otherwise, he would teach Comp Sci 289A. 21st century advancements in theoretical computer science.
I might do that next quarter, but it's the highest teaching.
Take him, Venkat. He's a great professor. Okay. Why do we need privacy? So this XKCD comic is probably Meka also showed this comic during his lecture for us on privacy. So here I am ripping it off. But basically, when you train predictive models on input from your users, it can leak information in unexpected ways. How and why? ML is a black box. We just need to make sure that it doesn't do this. Okay. So on a more real example, we're going to talk about something called the Netflix challenge. And so basically, sometime in the 2000s, what Netflix did is they had a recommendation algorithm challenge. And basically, the best recommendation algorithm that somebody could create on their data set that they release would get $1 million in prize money. So basically, every freaking researcher was trying to do this because $1 million is a lot of money, right? And so basically what Netflix did is they gave like a redacted data set. This is Netflix's data set. And they basically had a bunch of entries for each user. And each user contained information about how long they watched a movie for, all the movies they watched, their ratings for the movies, whether they liked it, information like that. And guess what? Yes, they took out all personal information associated with each user. So this is anonymous. If you look at this, you should not be able to figure out who the user is. In theory. Now, there's this great website called IMDb, where other users can leave non-anonymous reviews. And what a bunch of researchers did is, instead of focusing on the $1 million, they're like, wait, if I sue Netflix, I can make more than $1 million. So what they did is they found a way to correlate the Netflix anonymous data set with the IMDb reviews, and we're able to get the exact names of the people in certain parts of the data set. And guess what? Netflix canceled this challenge because of that, because the US government was after it after this. And so basically what happened is
researchers get money for suing Netflix.
I have no idea. You can read more. This is the Wikipedia article about it. But basically, this was called a correlation attack. You think your data set is completely anonymous, right? Like, take out all the possible personal information, nothing could possibly go wrong. We have other databases that we can associate things to. So this is something called a correlation attack. There's another version called a reconstruction attack, which is what it means. You can reconstruct parts of the data set even though they're redacted. And so the entire point is with differential privacy, both reconstruction and correlation attacks should not be humanly possible. So it's kind of weird how differential privacy will guarantee this, right? Even if I tell you I have other information that you don't know, differential privacy will make a guarantee that you will never figure it out with a certain probability, because everything is with a probability here. Okay, so we're going to start off with this. We're going to start off with a very simple example. Okay, I want to release an entire data set. And what we're going to do is we're going to compute the mean of this data set. So if I just release the entire data set to you, that is zero privacy. You have the exact raw data. For this example, let's just say each data point contains a 0 or a 1, binary classification. If I want to release the data in a fully private manner, I can just release to you garbage. At each entry, I'll just flip a coin to pick 0 or 1, right? And if your data is random, it's private, right? Because there's no correlation now. It's completely random. But let's kind of think about the implication of this. If I release the entire data set, my mean is very accurate. If I create randomness, my mean will be around 0.5, right? The expected value, that will be 0.5. That gives me no information about the data then. So privacy is going to have this balance between dealing with preserving the privacy of each individual user and also still making sure that our ML model is going to have accurate results. Because having privacy doesn't mean anything if you can't use it. Okay. So that leads us to our first algorithm called randomized response. So basically the entire point of randomized response is assume your data set is consisted of only zeros and ones. Okay. We're going to denote the original data set with xi, each point in our data set, xi. Xi is part of the set of 0 or 1. Here's what randomized response does. We modify each xi. We're going to denote that with xi hat, and we're going to say it's going to be the original value with probability 1/2 plus gamma. And we're going to say it's going to be 1 minus xi with probably 1/2 minus gamma. And basically what we just did is we formulated what we did in text above, right? If we have gamma equals 0, what happens here? Fully random. If we set gamma equals 1/2, what do we get?
The original.
We get the original data set. So now we basically constructed an algorithm where by changing the value of gamma, we get a different level of privacy, right? The lower the gamma value, the higher the privacy, right? Because we're getting closer and closer to fully random. So now with this algorithm, I also want to make a remark on the efficiency of this with respect to gamma. And this is why I said we're going to talk about only the mean. We're going to compute the difference between the true mean and the expected mean with random response. So in a data set composed of xi's till n, what is the true mean? It'll be x1 until xn divided by n. This is the true mean right here, okay? Now we want to compute the expected mean after running randomized response. So first, let's just compute the expected value of a single example, which is this, right? The expected value of xi hat. What is that?
1/2.
No.
Oh. Oh, like with respect.
Yeah. But I hope everybody here knows the definition of expectation. Actually, this is great. Usually I would have just written this answer because everybody has done probability. I can ask you guys to tell me what it should be. Are you actually going to try it too?
Yeah.
Okay.
Oh.
Wait, this is actually maybe better than having
1/2.
Cut that out too, please.
1/2 minus gamma plus 2 gamma xi. Is that this one?
Yes, that is exactly right. So Akash actually did the simplification for us as well, but this is just the expected value, right?
Yeah.
Into 1 minus xi, which is going to simplify it to what Akash said, which is 1/2 minus gamma plus 2 gamma xi. Okay. And now what I'm going to do is I'm going to rewrite this expected. I'm going to write everything in terms of xi now. I'm going to shift xi over to one side So xi is going to be in terms of the expected value of our new variable. Okay, so with some algebra here, what we're going to get is xi is the expectation of xi bar minus 1/2 minus gamma by 2 gamma. And now I have xi in terms of our new variables, and up here I have an expression for the mean in terms of the original data. So what does that mean? I can substitute all of this into this expression, okay? And this is just a lot of algebra that goes on, so I'm just going to rewrite it here. And so the estimate is what we'll call it, is as follows. We can bring the expectation outside because of the linearity of expectation. We're going to get x1 bar m minus 1/2 minus gamma by 2 gamma. Okay, so this is the expected value of the mean on our data after we really sit through running randomized response. Okay, and the reason I do this calculation is it's a fun and easy calculation to do. And basically what you will end up doing is you will use this calculation to get the following probability. You're welcome to search this up. We won't go into this right now. But the probability that the difference in our original mean is greater, the difference between our original mean and our release mean is greater than a difference epsilon is given by this formula. Okay. And you read this derivation I did above to actually be able to compute this probability properly. So what does this say? This is basically saying that there are two things here. The higher the gamma value, the larger this probability is going to be, right? The probability that we're farther away from the difference is going to be greater than epsilon will constantly be increasing.
So the larger the gamma value?
Or, sorry, the smaller the gamma value. Yes, the smaller the gamma value, the harder it is for us to be within a value of epsilon, right? And obviously, and so now what we can actually do is we can say, if I have a gamma value and I have a desired epsilon value, what is the number of samples I actually need to achieve this probability? So basically what I'm trying to say is differential privacy is also dependent on the number of samples we have in our data set. Because the more examples we have, the more privacy we can preserve, but still retain accuracy. And so as an example, suppose I say I want an epsilon accuracy of at least 75%. Let's go ahead and calculate what n value I need here. So remember, this is saying what is the probability that we are out of the 75% accuracy, right? So what we get is we have this should be less than or equal to epsilon times 4 gamma root n. The 4, for the reason I chose 75 is because the 4s will cancel for us pretty nicely. We get epsilon over.
Should the force cancel out? The force still there.
Yes, the 4 should cancel out. And wait. Yeah, I messed up my order of notation. Okay, I'm running out of space again. Zoom in a lot. And what we're going to find is you can do the algebra, but this. So the number of samples we need is going to be proportional to the epsilon value and the gamma value. Right? Which kind of makes sense. If you want really high accuracy and you want to preserve privacy, you need more samples. This will also make more sense when we define what privacy actually means. That is a different set of research papers. We just go with the canonical definition of privacy for now.
How did we get there? Just
Okay.
math-wise?
Okay, I think I probably wrote greater than or equal to sign wrong. So give me 1 sec. So the 4s cancel, and that's a great question, Akash.
Like, because it says less, like n has an upper bound, which feels weird.
This is saying n has an upper bound. Let me get back to that one. My notes are wrong. I know what the error is. It's a little bit more complicated than that.
Okay, if that's the bound, we can just.
That is the bound. Okay. And what we'll see is this actually sucks. Like crazy.
Oh,
Yes.
well.
I mean, it should make sense because we're literally just shifting and turning, twisting examples, right? We're like inverting the example when we have one.
Yeah.
And that's probably not the best way to preserve privacy by just inverting and giving completely wrong information. But that is when we get to something called the curator model. And so this is how most of privacy is preserved in machine learning. You have a query and answer mechanism. So your machine learning algorithm should ask you a question and you will provide it an answer. The person that provides the answer is called the curator. The curator will have access to the entire original database. And it is the curator's job to release an answer in a way that will preserve the privacy of the original database, if that makes sense. Because the curator will take in a question and give an answer, right? How the curator releases the answer is called a mechanism. The mechanism is quite literally usually just a function that will preserve the privacy. Okay. Any questions on this model? Now we get into how we say something is private. So this is the definition of privacy we'll follow. We can talk about this actually because there are not that many people here. Why this is a good definition of privacy. We can say something is private if we cannot tell if a user was originally part of the database. What does this mean to us? AKA, our answer should not change just because one user changes in our database. Now let's think about why this will actually preserve privacy. If you think about it a little, what is the highest level of privacy you can have? I should not know whether somebody was part of this set or not, right? Because if you don't know if they're part of the set or not, you can't make any conclusions about them. So for example, in the case of the Netflix challenge, you were able to correlate the fact that Bob, let's say, is in the Netflix dataset because IMDb has some information. But what we're saying is, hey, even if you remove this one entry, our answers will still be the same. So you can never make a claim that Bob was actually in the dataset. And therefore, you've satisfied user level privacy, if that makes sense, right? If you cannot tell whether somebody is part of this group or not, you cannot make a claim about that, right? Do you have a question about that? It's a little confusing. It takes some time to wrap your head around.
I was thinking at first it would be like, even if you know a user is there, you can't figure out anything else about them. But I guess this is stronger. Like if you don't know they're there, period. That's just bad.
And here's the hard part with that definition, right? Correlation attacks.
Yeah.
Like how you would then make an argument about preconditioning things on extra information, on any information set, which is very hard to do. So instead, what we say is, hey, you should not be able to tell whether I'm in this or not, because then you will never know anything, right?
Is it also bad if they know for sure you're not in the set?
Yes, it is.
Okay.
But not if you, those two are just like the not of each other, like in terms of an equivalent statement. So the point of that is, if you can't tell the user was in it, you can't tell the user was not, right?
Okay.
That's the entire point of that. Does that make sense? So that's basically the entire point of differential privacy. Now we get into the math notation of it. So first we define what a neighboring database is. In terms of terms, a neighboring database is a database that differs in exactly one row. So if we're thinking of a database of users, we're saying a neighboring database only has one different user, right? So if D and D1 are in the set of Xn, where X is in Rn, or I should say Rd here, then D and D1 are neighboring databases if and only if they differ by one row. And hopefully you can see why we want this definition, because we're talking about exactly one user not being in something or being part of the dataset. Okay. So then we get into the definition of privacy, specifically epsilon differential privacy. And what this basically says is a mechanism, so remember how we release our answer. So it takes in a database xn, and produces some output y, is considered epsilon differentially private if for all neighboring databases. So any like permutation of these databases where one user is removed and another user is added, the probabilities that the output stays the same is bounded. And it'll make more sense when I write the math notation down here. So D and D1, and for all possible outputs y. So we were basically saying for everything humanly possible here, the following probability statements will hold. So basically, what this is saying is you have two neighboring databases. The probability that your output is going to change should be very small with respect to e to the power of epsilon. So e to the power of epsilon here, you can think of it as the leeway we're giving us for our privacy. Oh, with this really small probability, they can change. Because then if you have a really small probability, it means nothing, right? Yeah. Because the probability of that event occurring is very low. And so just a couple of things. So that's the definition of epsilon differential privacy. We will use this statement. We'll say e to the power of epsilon is approximately 1 plus epsilon for very small values. Yeah. Hopefully that it's just a math thing. Yeah. And we will actually only use this once, and that is in proving that randomized response is epsilon is differentially private. Okay. Any questions about the definition of differential privacy and neighboring databases? I can give one more example that may help. And basically what we're saying is if you have a histogram, right, where these are the probabilities of an event occurring, and this is like the value, something like this. The idea is if you were to copy and paste this histogram for a neighboring database, X prime, the heights of the histogram, like the differences in each bar, and the heights should not be greater than e to the power of epsilon.
Well, like how much they change.
Yeah, how much they change should not be greater than e to the power of epsilon. Okay. So the change I will allow for each bar will be e to the power of epsilon. Okay. So now, if you remember randomized response, we're now going to prove that it is actually differentially private. And specifically for releasing the mean. All of this is in the context of just releasing the mean of a data set. And so already the math is like getting up there notation heavy. So you can imagine when we start talking about other types of queries, we won't really get into the math of those. The math is very similar, but the mean is a very easy way to work. So we're going to say for all possible values, A and R. So A is our possible output, right? How is A going to change here? Remember neighboring databases. So if xi is equal to xi prime, so this is, let's say in database 1, or that's in the original database, and this is in the neighboring database, right? If these are equal, our A value stays the same. Hopefully that makes sense, right?
Is A the output?
A is the output.
Okay.
A is the output here, right? Because we're not changing the value. And so now, what is the probability? This is the probability that we're going to want to find. The probability that our first database outputs A and our neighboring database also outputs A. We're going to use the fact that if the values are the same, we're good. If the values are different, we're not good. So what is the probability in here when we release this that our value is going to stay the same? 1/2 gamma. And what we're going to say is this is going to be lower bounded. So this probability can be less than this.
Okay.
The maximum possible probability will be when we actually change this value, right?
Yeah.
So we get 1/2 minus gamma. And through some algebra, you're going to get this. And if you remember, the reason we said 1 plus epsilon for very small values is equal to e to the power of epsilon is just to say this is approximately this. And basically, once you get this ratio of probabilities to be in some form of e to the power of this, you can say it's epsilon differentially private, right? Just follows from the definition, because we can just divide the probabilities on each side. So we're going to say that randomized response is big O of gamma differentially private, because we're just going to evaluate this as big O. Okay. And so basically, hopefully, we're kind of getting the feeling that randomized response has this privacy guarantee, but it's not really great for the accuracy, right? We need a really high number of samples to preserve accuracy. So maybe there's something better that we can do. And so there are two things that we can generally do. One is something called input perturbation. So input perturbation means we add noise to each value in our data set and then compute whatever we want to compute, right? So if you adding some noise to your original data and then you compute what you want to compute, hopefully you won't be able to reverse that process and figure out what noise was added to get the actual information.
Oh, okay.
The other option is we compute the true value and then we add noise to whatever output is. So in the example of a mean, you add noise to all of your x values and then you calculate the mean versus calculating the mean and adding noise to just the mean. Okay. So those are the two mechanisms, like the two branches where we can take to kind of preserve privacy. And so each of those would require a different form of like the proof mechanism used, right? Okay. So how many of you know the Laplacian distribution? Okay, well, we know how probability distributions work. So I'm just going to write the following thing. This is literally the definition of the Laplacian distribution. And this is assuming a variance of B and a mean of 0. Okay. This is the probability distribution for the Laplacian.
What does it look like?
It's a great question. You can search it up. This meeting is being recorded.
It's just like this and just the point at the top.
Yeah.
Let's see. I believe it'll look very similar to the Gaussian distribution, actually. If I recall correctly. Yes, it's so I don't know if you all can see my screen that well,
Yes.
but basically,
It's a little pointier.
so it's very pointy.
Okay.
And actually, that's a good question to ask, because that's like an approximate thing of a Laplacian distribution.
Yeah.
Your normal distribution would look like something like this. And so what you can see is there's like the Laplacian distribution, the probabilities are very concentrated. And we would like that because then it's hard to tell the differences. But whereas with the normal distribution, you can tell like the probability of something happening is far greater on the outside, right? And so that's why in the beginning, I said we were going to talk about approximate differential privacy. And that is where we like the Gaussian distribution. It'll create an approximation guarantee compared to Laplacian distribution, which is much harder, right? It's much more narrow and the variation is much smaller. Okay. And so this is the Laplacian mechanism. And what the Laplacian mechanism guarantees is it guarantees output perturbation. So Laplacian mechanism does output perturbation. So after you compute something, you add your noise, right? So you have a computation. So we do f of x plus adding noise. And this noise is derived from the Laplacian distribution. Any questions so far?
Oh, so we don't put like our input into the Laplacian thing. We just use it to make noise.
We use it to make noise.
Okay.
So this is going to be our mechanism. So our mechanism x is going to equal the actual computation f of x plus some noise z. Does that make sense? And then for a neighboring database, this is going to be the computation. Z here is noise from the Laplacian distribution.
But wouldn't that make it so that because it's always very close to 0, you just like add nothing?
Not necessarily.
Okay.
The idea for this is even though you're adding the small amount of noise, you should not be able to, basically every proof in differential privacy is going to compare the probabilities to each other. And as long as the difference in the probabilities, or the ratio between the probabilities, is very small, that's all we care about. So you can get away with adding really small amounts of noise to your data and still keeping this distribution, that's great. To Jordan's question, you will have to add more noise depending on the size of your data set. So when we say, oh, you're adding very little noise, how is this guaranteeing privacy? Yes, you can add very little noise for a very large data set. But as your data set becomes smaller, it becomes easier to indicate outliers. So then you have to add more noise to compensate for those outliers. That's probably like the more intuitive way to think about that. And we'll get into actually how we determine adding noise for the Laplacian distribution. It's something called sensitivity of a function, but we're also going to demonstrate that in this example. So again, we're going to go back to the mean, okay? And I'm going to ask this one question. If we're dealing with only zeros and ones, what is the maximum difference in the mean for n samples between two neighboring databases? Do you want to explain why?
You can at most change from 0 to 1.
You can at most change from a 0 to 1. So the maximum difference between f of x prime and f of x is going to be 1 over n. Does that make sense?
Yeah.
And remember, this is only for the mean. And what we're going to show is this difference, the maximum difference between the output of two functions, is called the sensitivity of the function.
Okay.
And that will come in handy when we talk about the generalized Laplacian noise beyond just the mean. Okay. With all of that out of the way, let's now prove that this satisfies our definition of differential privacy. So what we're looking at is the following. What is the probability of this? Probability of this is the probability of f of x plus z equaling a. And this is equal to the probability that z is equal to a minus f of x. And we have this definition of probability right here. So we're going to go ahead and substitute that in. And what we're going to get is we're going to get 1 over 2b e to the power of this. Okay, well, I'm just going to continue up here for now. And then I'll write these notes later for everybody. We are going to show that epsilon differential privacy has a post-processing guarantee. So basically, what this means is, hey, I'm telling you based on the output and the answers I give you, you're not going to be able to tell whether something was in the database or not. But now, say I had some other function that I can apply to your output. I'm going to prove that that also still has epsilon differential privacy. Okay. And in many ways, you can think of this as the proof for why correlation attack may not work, right? Because if you define like another function that is dependent on your output to create something, we're going to show that this is also within the definition of epsilon differential privacy. Okay, so basically, right here. So we're going to have a mechanism M that goes from n examples to y. And we're going to take another function that will say y takes in y and goes to z. Okay. This can be any function, right? We're not making any claim about the function or anything here, which is why this proof will work. And if we compose these two together, this is going to go from xn to z. Okay. And so now what we're going to say is for every z in this, probability that f composed, right, is going to be this. It'll be for all y such that, where's my eraser? This is true. Does that line make sense? Any questions so far? Do you have any questions, Jordan? Brent has no idea what's going on, I think. Okay. Now, what do we say? We said that our mechanism is epsilon differentially private, right? That is like the premise. And so what is this saying? This is always going to be less than or equal to right? Note that now we have an X prime here, right? Because we're writing this in terms of a neighboring database. And just how we went from this line to this line, we can revert this process back and go like this. I'm gonna just forego writing the bottom of the sigma notation because it's repetitive. So do we get how we kind of went from this line to this line? We're just using the definition of the composition there, right?
And we can do the same thing to get the lower bound.
Yes. And like this is basically saying it has to satisfy either or. Really. Because if it satisfies that, either the power of minus that will also satisfy. So this is the proof for, hey, if I have any other function that I apply to this, I'm going to be differentially private. Okay. Now, it's really not great to only assume that only one value will be changing in your database. What we can say is we're going to have k values that will be different. And so that is when we go into something called group privacy. If you change a group in your database, we should still be able to preserve privacy and not tell whether a group was part of the database or not, right? So let's say I had a set of, let's say I had like a really large data set and like most people are like located here. And let's say I have like a group of people that are out here, outliers. What we're saying is we don't want people to know that the outliers are part of our data set. We want to preserve the privacy of this entire group of people, not just one outlier, but an entire group of outliers here. And so basically, the way we can formulate this is if you have a database X and XK, which has K different rows compared to X. We can write this in terms of a telescoping series. What I mean by that is we can go from X to X1, where we change exactly one row. From X1, we can change another row and get to X2. And we can repeat this process K times to get to XK. So each time in this process, we're just changing one row. And now we have a database with K different rows. And so what we're going to say is the probability that M of X0, our starting database, equals Y is less than or will be this. X1 equals Y, right? This is, we're saying, we're just applying the definition of differential privacy for each arrow. And so for, in the case of X1 and X2, getting ahead of myself there. Okay. And you kind of continue this telescoping series down. Okay. This K and N here, we're going to use as the same thing. And so hopefully you can see that, oh, I can place this into this, and I'm going to get e to the power of epsilon times e to the power of epsilon times probability of M of X2 equals Y with respect to X0. And you keep doing this, what you're going to get is that the probability of M of X0, what is the time, by the way? 7:12. Okay, that's just from the telescoping series. And so now we've shown that if you have a mechanism that is differentially private for K group differential privacy, in this case, it'll be epsilon K differentially private. So, but basically what this is also saying is you have to add more noise. noise as well, right? When you have to do group privacy, which should make intuitive sense. It's harder to preserve that. Okay. Now, so far we've only discussed the mean. And like, yes, this does generalize to any other function, but it would probably be nice to have an actual example of something else. And so I'm just going to read off this part. There's not much math to this. We're just going to provide definitions for now. So we're going to talk about something called counting queries. And basically what a counting query is, we want to reveal the number of users for a certain record, right? So let's say you have like 6 different types of cancers. You want to reveal how many people have each type of cancer. Still, like when you think of an ML model, like we require way more information, but we're slowly building up to that. And basically what we're saying is the sensitivity for that, right, between 2 neighboring databases will always be one, because you can remove somebody from a certain group and add them to a different group. So in that case, the noise you want to add will be 1 over epsilon in terms of the Laplacian mechanism, right? Remember, the noise we're adding is the sensitivity of the function divided by epsilon. So for a counting query, the sensitivity is 1. The difference will always be 1. Does that make sense? Okay. Now, if you combine the proof we did for composing like group privacy, and you said, I want to do k counting queries, right? So I'm going to get like k different counts here. You have to add noise of k over epsilon to preserve privacy. So next thing to note, as we make our queries more complicated, we're adding more and more noise here. Okay. And there is also something called a histogram query. This, I'm just going to verbally say this because it has a really nice property. So if you want to produce histogram queries of each user within one of k groups, you actually only have to add 2 over epsilon noise. Okay. The proof for that is also in another research paper, which you will do in Make Us Class 3 tickets, not in Theory Track today. Okay. And so the last thing we have to talk about for Laplacian noise is how accurate is it? Okay. And so whenever we talk about accuracy, we're going to talk about the probability that it is out of a certain range, right? So the probability that the noise we're adding z is going to be greater than or equal to b times t, right? B times t is the range we're allowing. So before in randomized response, we were calling this epsilon. We want our answers to be within an epsilon. This is the probability that we're going to be out of this range. And basically, this is always bounded by e to the power of minus t. This is from the definition of the Laplacian mechanism, by the way. Right, so if we want to have, accuracy of b times t, this is the accuracy we're going to get. If we're adding this much noise, so b times t, this is the accuracy we're going to get. So not great, but it's significantly better than randomized response. Okay. So we proved all of that. We also proved the composition. What the composition theorem basically says is if I have k different mechanisms that are epsilon differentially private, the composition of them will also be epsilon differential private. Okay. I do want to do online learning for you guys because I think you guys will actually appreciate that more than more probability. Okay. Approximate differential privacy. I'm going to not write the notation for this either. So if you remember for differential privacy, we say that we have to be exponentially close. The probabilities have to be exponentially close to each other, right? Because we have e to the power of epsilon. Approximate differential privacy adds, like, you can think of it as a bias to this and says you need to be multiplicatively close, but you can also be within a range, like, let's say here, gamma. And so what we're saying is, where did I put that marker?
Oh, you can be a certain ratio away or a certain difference away.
Yeah, you can be a certain difference away.
Okay.
Where did the marker go? Oh. That's like words for us. But I'm just gonna write the probability plus some value. Yes. Okay. So this obviously relaxes it because you say you have to be multiplicatively close, but you get this leeway of gamma. And so obviously, the smaller the gamma, the closer you are to pure differential privacy. The larger the gamma value, the farther you are from pure differential privacy. Gamma equals 0 is pure differential privacy. Yeah. And so basically then what we can do is we can, instead of here where we're dealing with a Laplacian distribution, we can use a Gaussian distribution. And what we'll find is a Gaussian distribution doesn't satisfy epsilon differential privacy, but it satisfies approximate differential privacy. Okay. And what we'll see is the reason we like this is when we're talking about the number of samples we need, the Gaussian distribution will add significantly less noise, even if we have a smaller number of samples. And that makes us happy because less noise means we're less farther off. And that gets us into the composition theorems, the basic and advanced composition theorem. And so what I'm just going to write here is the advanced composition theorem. And so generally, when we're doing differential privacy, we're going to have multiple mechanisms that we're going to have to chain together, right? Because each mechanism is only producing like one output. So if I have a bunch of mechanisms that are epsilon differentially private, so these are pure epsilon differentially private, the chaining of them will be the following kind of theorem. Okay. And so this is approximate differential privacy. Okay. So it's a tuple because one is your epsilon value and the other is your gamma value. Okay. So the first half of the tuple is your epsilon value. The second half of your tuple is your gamma value. Okay. And basically what this is saying is you get a better, you can use less noise with this. Okay. Even if you have a bunch of mechanisms that are differentially private. And so that is the advanced composition theorem. This is used very often in differential privacy. Like any proof in differential privacy will basically rely on the advanced composition theorem now, because it simplifies what we have to do so much. Okay. Now we can talk about how we can use this in actual machine learning. So far we've talked about this really nice function where you can just query it and ask it. But all machine learning is empirical risk minimization, right? We're constructing a loss function and we're trying to minimize that. And I can ask you this, but what is the relationship between the mean and a loss function? There's barely any. You can't do anything if you're just saying, oh, I'm preserving the mean, right? That doesn't work for machine learning. So what we actually end up doing is we have now 4 categories of how we can preserve privacy for ML. One is we compute the optimal values and then add noise. So you run your machine learning algorithm, compute the data value, the optimal data value, and you add noise to the data value. Now you can preserve privacy with the same guarantees we were giving the proofs. Yeah. Follow a very similar flavor there. Input perturbation. You add noise to your data set, and then you compute everything. Much harder to prove. Objective perturbation. You add noise to the loss function. Okay. And then you also have gradient perturbation, which is you add noise to each gradient computation. Now, let's make some remarks about each of these. Output perturbation has some very nice things about the loss function. So suppose your loss function is very steep. So here's data. So as you add noise to your data, if your loss function is spiking like crazy, that's not good. So you can't really preserve privacy and then have a good ML model. But in the first place, is this really the data value we want to have where it's really sensitive to our inputs? Probably not. So what we can make a claim about is if we have a nicer loss function, or at a minimum for a little bit longer, maybe not optimal all the time, but we can add noise, we'll still be able to preserve privacy. And our model will perform well. So that is a remark about finding a good data value.
So
and how
perturbation is at every gradient step.
Sorry, great.
After do you compute the model first,
Mhm.
and then you add noise to the very end, and you do nothing afterwards?
Yes.
I see. Okay.
And basically, if you go back to the curator model, now our ML, basically the question for our ML algorithm is give me the optimal data values.
Yeah.
If that makes sense. That is the question our ML algorithm is going to ask the curator.
Yeah.
Okay.
Yeah. Well, Well, I guess like if you just add the noise at the end, how are you guaranteeing that to begin with the theta was at a flat local minimum?
Oh, this doesn't guarantee anything.
Oh,
This is a remark about
if it works.
If it works, hey, like, so if you look at like deep learning and stuff, you like minimum that are like not like this, right? And so what we're basically making claim is we find really nice minimum like this, we can also preserve privacy a little bit more easily,
I see.
while not affecting the accuracy of our model. Input perturbation, you're just adding noise to your entire data set and then sending that out. Objective perturbation is adding noise to your loss function. Okay. And so basically now the question you're asking is, what is my loss at this value of theta? And you add noise to that. Okay. I'm basically kind of talking about this in terms of the curator model. I'm telling you what the question is in each of these cases. Gradient perturbation is you add noise to the gradient computation itself. So instead of asking what is the loss value, you're asking what is the gradient at this position. Now, some of you may remark this is very similar to SGD, right? Because stochastic gradient descent, you're just choosing like a random sample. And in theory, that's also naturally injecting noise. Yeah. It's not strong enough to guarantee epsilon differential privacy though. But you'll see like a lot of things in ML are kind of related to each other in that way. Also, when we talk about like adversarial attacks before, one of the things we would like to do is we can make a model more robust by adding more noise to it. That's kind of what's happening here. So adding noise has a lot of interesting things and benefits and sometimes cons in machine learning. Okay, so I wanted to make also one remark about gradient perturbation. What is the sensitivity of the gradient? Remember the example where I talked about the set of all real numbers? It's massive. The noise we're adding, massive. So that's why I said SGD doesn't really do that, right? It won't satisfy that. So there is this thing though called gradient clipping. We restrict our gradients to be within a certain set of values, right? We also do this with vanishing and exploding gradients, right? We clip our gradients so that they don't get too big or they don't get too small. Guess what that allows us to do? It bounds our noise for us as well. Okay, so some interesting ties here and there. Any questions about differential privacy? And so this slide is basically how differential privacy is actually used in ML. The previous slides are the mathematics of basic probability, or basic probability in the field of differential privacy. And then, yes, basically you just take for differentially private stochastic gradient descent, take the gradient descent algorithm and add Gaussian noise at each step. So there are also other forms of differential privacy, not epsilon differential privacy. We have something called labeled differential privacy, user level differential privacy, and shuffle differential privacy. Shuffle differential privacy is probably like the more interesting one out of these, but I don't know too much about them. I haven't studied them, but there are other forms of differential privacy out there. Okay, any questions about differential privacy, comments, questions, concerns, stuff like that? No? Okay. I'm gonna drink some water and then we'll talk about online learning, which is the hard stuff. For online learning, I'm not going to do proofs with you guys. I'm going to motivate, actually, I think Jordan may enjoy this. I'm gonna motivate the algorithm for online learning. And also AdaBoost. So how many of you know about AdaBoost? Okay. Heard of it. So basically, in machine learning, we can ensemble models together. We can train a bunch of different models, and then we can somehow weight their averages and their responses together to create a better output. Yeah. And so how do you weight that, and how do you come up with those weights is what AdaBoost does. Okay. And also what AdaBoost does is it'll train on a certain subset of samples. Mm-hmm. Now, what we're actually going to notice is the proof for ensembling in machine learning is dependent on online learning. And I'll define all of that, and then hopefully we'll get like a nice algorithm. And this algorithm is actually used also beyond ML. It's a very applicable algorithm. And we also can make some really nice remarks about pseudo-randomness and randomness and the requirement of randomness for achieving the best possible result.
Does boosting in general refer to like how you weight models like gradient boosting?
I'm not too sure about gradient boosting. I probably would want to read up before I make a comment on that because I'm not too sure. Maybe Jordan knows. But I'm not boosting here. We're AdaBoost and boosting. We're going to talk in terms of how we figure out the models that we want to use, how we select the training samples that we want to use, and then how we weight those together. Okay, so yeah. There are no slides for online learning. So in classical ML, we have this actually very unreasonable thing, in my opinion, and that's saying that we have access to all of the data at the same time. Now, hear me out. Let me take a recommendation algorithm for you. If you create a new YouTube account, it has zero information about you, besides maybe your geographic location and like all sorts of other small metrics, but it doesn't have anything about your personal taste. So how are you going to go about creating this ML algorithm? Are we going to give you really crappy recommendations for the first year of you using YouTube? And then hopefully we have like a data set of like 200,000 videos and things that you've liked and what you spend more time on and then compute stuff for you? No. We want you to get reeled in. So we're going to want to make a model as best as possible at every time step. So with online learning, what we're basically saying is we don't get to see all the data at once. At each time step t, we let you have one new sample of data. Okay, and so we're going to start out with this assumption. So we're going to say that there exists some function, there exists an optimal function that we are trying to find. And we're trying to get closer to this function. This is the optimal function. We will remove this constraint, maybe not in this workshop. We'll see. This is the optimal function. And basically, each day we want to get closer to this optimal function. That is what online learning is. How many of you, actually, before I say that, when we want to get to our optimal function, we want to take the least number of steps. Or in other words, we want to make the least number of mistakes. So online learning is what we call a mistake-bounded model. We want to reduce the number of mistakes we made while trying to get to the optimal value, right? The more mistakes we make, worse things are going to be for us. How many of you know about perceptron? Okay. So what is perceptron? You have positives and negatives, and you create a line of best fit that separates them, or margining your half space. Now, perceptron is actually started off as an online learning algorithm. Now let's think about it. Day one, you get one sample. You draw a line. On day two, you get another sample. You adjust your line, right? And so when we teach perceptron, we say, here's your entire data set. Now compute the best line. But in reality, what we can do is we can introduce each data point one at a time, and we keep shifting our line. And so basically, perceptron is a mistake-bounded model. And it is an online learning algorithm, okay? And what we're going to say is, if you have, actually, let me see if I can draw this. If I have a line, what the half space is you can think of it as like a boundary where no other value will exist, right? So all of our minuses will be on this side. They'll be outside of this blue region, and the pluses will be all over here. And basically what we can say is we define this distance, let's say, to be gamma. There's a proof that will say the perceptron will make at most 1 over gamma squared plus 1 mistakes, where gamma is this margin of the optimal line. This is our first online learning algorithm, perceptron. I'm not going to go into the details of this proof because I do want to get to ensembling. I can send you guys the proof, though. It's actually literally right here. It's not too bad, but it will take a bit to figure out. So that is like our first online learning algorithm. And as a remark to Jordan, maybe, perceptron has another way of being thought of, not just as in neural networks and as an online learning algorithm, but it's actually just SGD with hint loss. And I will let you contemplate that one for a bit. Now, moving on, perceptron's really cool. Now we get to do what you quant people love doing. Predicting the stock market is what we're going to talk about now.
That seems targeted.
I wonder why. No, but so basically, on Wall Street, you have a bunch of different investors. All these big guys being like, I'm the best at this. I know what's going to come next. You have a bunch of experts. Now, us common folk, we're going to listen to the experts, right? But what is our actual goal? We want to figure out who the best expert is, and we want to listen to the best expert. So now I'm going to talk about kind of where ensembling will come from. You have the experts. So let's say you have like 20 Wall Street experts, and they're telling you which stocks to invest in. Your goal is to figure out which one of them is the best expert. Each day you get to know whether they made the right decision or the wrong decision. My question is, design an algorithm that will tell me who the best expert is within a certain number of mistakes. Think about it. It'll take maybe like 2 minutes to think about it.
You chose the wrong expert.
You let's say you invest in a stock, right? The expert will say short the stock, meaning the stock is going to go down, or invest in it, the stock is going to go up. Each day you find out whether the stock went up or down.
Oh.
How am I going to determine the best expert?
And every day you get to see what each expert has said and what the results ends up being.
Yep. And all of this is predicated under the fact that there is a best expert. There is one person who will always get everything right. Okay. And what we're going to do, hopefully I get a chance to talk about the relaxation of that, which is very important. But yeah, take a minute, think about it, and then we'll talk. Or actually, why don't we just hear the ideas for a bit?
Well, first day you got to randomly choose. You have no information yet. And second day, you want to narrow it down to the people who picked it correctly the first day.
Yes.
And you just keep picking the people who have gotten correct.
Sure.
It's a greedy algorithm.
Greedy algorithm, right idea. Now I'm going to ask, how do you pick the expert that you follow for that day? Right? You need to choose somebody to follow. Remember, we're only saying the stock will go up or down. So there are two options here. How do you pick which one to follow? Let's say on the first day, right? How are you going to pick which expert? Maybe randomness is not the best idea, right? Maybe there's something else that we can do.
What information do we have?
You can follow the majority of the experts. So instead of picking just one random expert, you say, I'm going to follow the majority of experts that are doing this. Now, guess what happens here? I'm just going to verbally talk about this. The proof is you'll kind of get the idea of this. But when you follow a majority, at least half of them have to swing one way. So let's think about it like this. If you follow a majority and the majority is wrong, you eliminate half of your experts.
More than half.
You eliminate more than half of your experts. But if the majority is right, you didn't make a mistake, so you're happy. So each time you make a mistake, your samples are decreasing by 1/2. And so now the number of mistakes you make is actually bounded by a logarithm. Okay. I really wish I had time to actually write the proof for this, but the proofs get a little involved.
Yeah.
But that is called follow the majority. You are following the majority each day, and you cut out the people that are wrong. And so basically what you say is, after a certain number of mistakes, you're bound to have the right expert, the infallible expert. Okay. And so, if you think about this in terms of an ML model, you have like 20 different ML models. You say one is always getting 100% accuracy. This is how you can determine it, right? Now, the idea of having an infallible expert, somebody who is always right, it's not true. Nobody on Wall Street is always right. So now, let's say I ask you to design an algorithm where there is no infallible expert, but you need to figure out the expert with the least loss, the one that makes the smallest number of mistakes. How do I do that? We can debate it for a minute. So, talk about that. Any ideas? So remember, when we had an infallible expert, we're able to just cut people out. But now, just because somebody makes a mistake doesn't mean we can cut them out.
Probably just change the weighting of how much people.
Yes. We have something called the weighted majority algorithm now. And so weighted majority is exactly what you said. Each day somebody makes a mistake, you reduce their weight. Each day they make a correct decision, you increase their weight.
And you pick.
And you pick the probability with respect to the weights. You add up all of the weights, and then you pick which one you follow based on that probability. Okay. And basically, there's a theorem that will go as follows. I will write this theorem for you all here. But your loss, L of t, will always be less than or equal to 2.4 times the loss of the best expert.
2.4.
Yes. Log base 2 of the number of days you existed for. Okay. there's a proof for this. I will send you my notes about it. Now, we will talk about something called regret.
Yeah.
I have a lot of those. Sure, hopefully other people have a lot of those. Maybe not. But hopefully the goal for everyone should be to have zero regret. And so what we're going to design is we want to design a zero regret algorithm. Okay. And basically what this means is as the number of days progresses, you want to have zero regret. So if you have a function that gives you your regret, like in this case, say regret is the number of mistakes you're making, the regret over t divided by the number of days should equal 0 as t goes to infinity. Okay. So as your number of days goes exponentially large, you want to say, I'm not going to be making mistakes anymore. Now, another proof that is in my notes that we do not have time for, but I would say, is follow the majority is not a no regret algorithm. Even though it seems like it seems like, oh, your regret will be going to 0. It is not a no regret algorithm. You will always have some amount of regret. And there's another research paper about the following proof. There exists no deterministic algorithm that will achieve no regret. And I can kind of tell you about the proof for that in this following way. Suppose I'm an all-seeing being. And I know when you're a deterministic algorithm, I know how you'll respond to every input I give you. I can just change the output to be the exact opposite of your input. And that is why a deterministic algorithm will never achieve no regret. Okay, that makes sense. Because I will always be able to tell you, if I can change the future, for example, right? If you're predicting, every time you predict a 0, I will change the prediction to be a 1, like the actual prediction to be a 1. So therefore, there exists some sequence of input and output where I can prove you wrong. Okay. And that is why a deterministic algorithm sucks. So what we need is a randomized algorithm. And that is where we transform follow the majority or weighted majority into something called the multiplicative weights method. Okay. And so if you recall with the majority thing, we were just summing up the weights and we pick the one which has the higher weight, right? We sum each thing. Now instead we're going to pick with a probability with respect to the weights. And so that is how we introduce the randomness. We're going to pick with a probability with respect to the weights. And for my own sake, so I'm not writing this out, here we go. It's much easier to talk about. So right here is the multiplicative weights method.
Yes, that's crazy.
Oh, we do more too. There's
Yeah.
PCA, there's graphical models.
It's not real.
It's very real.
Base.
Oh, what else? We did some other stuff too. But please note that this was done over the span of like 5 lectures, and I'm doing it in 10 minutes. So that's why I cannot give you the proofs, or like I'm not letting you guys think about it. But basically, this is what a multiplicative weights does, right? Instead of saying, oh, I'm always going to follow the majority, I will follow the majority with respect to its probability. And now the entire argument about being like, hey, I know what you're going to do, so I'm going to change like things to be wrong doesn't hold, right? Because you can't make that claim. And so multiplicative weights is a no regret algorithm. And yeah, let's not worry about that proof. But you will prove that multiplicative weights is a no regret algorithm. And for those of you who have seen the AdaBoost algorithm, cough, cough, Jordan, you will realize this is literally AdaBoost. And so in Cal's class and in 146, he will make a claim about weak learners, or in multiplicative weights, the experts, and how if you have a series of them, you can always construct something that will do better than each individual expert. That is the following proof here. Okay. So one remark: multiplicative weights is not even like an ML algorithm. It's used almost everywhere. So basically, here are some of the things where it's done: online learning, portfolio management, and graphical models. Multiplicative weights is used. Solving semi-definite programs, MWM is used. Solving linear programs, multiplicative weights is used. So this algorithm is not actually just a machine learning algorithm. It's a generalized algorithm that is used very often. And so basically, that gets us into AdaBoost, where we are transforming multiplicative weights to specifically work for machine learning. Okay. And basically, what happens is, and now your experts are your different ML models, and you're going to be training them on different sample sizes and changing the probabilities depending on how they do on those different samples. And that allows us to take a lot of the provable properties of multiplicative weights and the things it'll achieve and apply them. And so what we will get is this. And so what we're going to say is we can have AdaBoost achieve this level of accuracy given the amount of time is this, and gamma and delta here are the rates and the learning abilities of the weak learners. So basically what that says is if I give you a set of 70% weak learners, they all have 70% accuracy. There is a way to construct an ensemble of these weak learners to get, let's say, 80% accuracy, given these preconditions. And that is what AdaBoost does. And it uses multiplicative weights as its proof for that. So that is online learning. We didn't have PCA on the schedule, so we won't do PCA. But we will take questions, or if you want me to do a proof for online learning, we can do that. But any questions about online learning, differential privacy? I know you two weren't here for optimization. So if you have any questions about optimization techniques or optimizers or PCA or graphical models, I can answer those from a theory standpoint.
Optimization, like at all?
Like convex optimization, yeah. Like I could give you like some sort of idea on where things should go. And hopefully in terms of like gradient descent and stuff like that, but we can try. Principal component analysis. So imagine I give you a 1,000-dimensional data set. The probability that all 1,000 dimensions are actually useful there,
Very low.
very low.
Oh, so you're just finding these.
And so we want to find the useful ones. And I'll make a remark about that too as well. Finding the useful ones is very intensive, actually. And so when you study PCA, you will actually say you need to design an algorithm to do that is more efficient, but will get the right PCA vectors with a certain accuracy. And that method is called power iteration. And you will prove that power iteration will do what it says.
Yeah. And like PCA theoretically will get you the best like vectors. And the best thing is IT also ranks it. It's just here directions that's like the most variance and all the way to the direction with the least variance. Like if you want to extract some information, you just worry about the first few vectors. But sometimes people use PCA to refer things also to like stuff like problem coders and stuff like that, where it's like you're not necessarily learning the vectors directly, but you're just learning like a way to represent high dimensional data into much lower dimensional data.
For reference, with PCA, like we talked about the Netflix challenge, the Netflix engineers didn't use PCA for their baseline. They just forgot about PCA. And guess what? Just applying PCA by itself got 4% better accuracy on like the models, like automatically. That was like $1 million gone because they didn't do PCA.
Yeah.
FYI. So like, it was brutal for them. PCA also is really important in genomics and things like that. If you run PCA actually on genomic sequence data, you will find that there's a correlation. Like I think 23andMe did a study where they ran PCA, and basically the different like principal component vectors of the DNA sequences were closer together based on the geographic location. So the principal components vary based on the geographic location, and you could tell that just from PCA, nothing else. You could run PCA and then a clustering thing, and you would get that answer. So PCA is very powerful in that regard. Maybe I am not enrolled in the class. I didn't first pass it. If I can get in, I'll probably do it. Yes. Yeah, PCA is just all linear algebra, by the way. Differential privacy is all probability. Graphical models is mainly probability. You guys actually may like graphical models because there's you have to solve a maximum spanning tree problem to actually yeah, there's this algorithm that will be able to reconstruct any tree, like graphical structure for you. It's called the Chow-Liu algorithm. And the proof for that and like the algorithm itself requires you to realize that you need a maximum spanning tree. Yes. Yeah. So yes. Any questions about constrained optimization, convex sets? Can talk about that. Optimizers, Atom, RMS prop, stuff like that.
What's the coolest thing out of all the things you said?
Like for optimizers? Okay, personally, I won't say the optimizer part. I think constrained optimization is really cool. I will get on my soapbox about constrained optimization. I think it is probably the coolest thing to exist. Like just the idea of projecting back into a set and then still being able to make theoretical guarantees about it. It's really cool. And it's used in adversarial attacks. You need constrained optimization. And then some interesting stuff actually, maybe for you guys is if you know about like the L1 and L2 norms. So sometimes when you optimize, you'll optimize based on the L2 norm. But you also do have to run like these algorithms for graphical models and stuff like that. And there actually exists better norms for graphical models other than like the L2 Euclidean distance norm. And so that is something you could explore as well. There's also like some techniques about when you have to optimize, you have like this loss landscape and you need to find the minimum value of a function, right? Sometimes that can be really hard to do. So we say is we will transform the landscape to make it easier to optimize in certain ways. So there's stuff like that. But yeah. Yeah, any other questions, comments, concerns? You should really take 260B. You should really take 260B. Just email him. Email him.
I'll tell you my schedule. I don't think I can handle 260B right now, unless I draw something.
Have you? Yeah. I mean, you have the math background for it. That's the thing. This is more so like a math class than like a math plus algorithms class than it is like an ML class. Okay, it's just like your algorithms are like ML focused. Oh, no. Oh. Actually, you're a sophomore. You have time.
Yeah. Wait, I'm on the wait list. I might just not get it. Oh.
Let's see. Yeah, so I will say this graphical model stuff is really difficult. Okay. There's a reason I didn't offer to teach like the theory of graphical models in workshops this quarter, because I did not understand his last two lectures like at all.
That's what Mecca did.
Yeah. But like I can show you like everything else is completed in my notes except the graphical models portion. Let me find the tree. Yeah, well, basically. Oh yeah. Here's a Chow-Liu algorithm. So basically, actually, if you read the titles, this is the baby Chow-Liu algorithm. So we make a couple of assumptions, and then we don't even write the full grown-up Chow-Liu algorithm. But yeah, the baby Chow-Liu does the minimum spanning tree stuff if you're interested. Yeah. Any other questions? Go back to differential privacy. Okay, good. Because I don't think I could answer any more questions. Yeah, so hopefully you learned what ensembling and add a boost do and where they come from. But thank you, Jordan, for letting me be on my soapbox for 2 hours. We're gonna have to cut out parts of this thing though.
I don't look forward to editing this. This could be this fully like a 10-minute portion. It's just like, yeah, the recording is completely unusable because of the whole thing.
Oh yeah.
Leave everything.
No, I can't do that.
I could give it to you and you can edit it.
No, I'm okay. You see, I'm just an officer, Jordan. You and Jackson are president and director, you know? You have more
not for long.
Yes, but you have more responsibility.
Not for long.
I love you, Jordan.
For me, I get too pressured into being
Oh, that's crazy.
Oh yes. The other thing I wanted to mention is I skipped over this thing called the exponential mechanism. And this is like an even better version of the Laplacian mechanism, but it defines something called a utility function. So basically, if you think of this as like when you're trying to buy a product, like what is the utility of buying this product at this price? And you have a function that determines that. This basically preserves privacy for that. So you can think of it like we're not even dealing with like counting queries anymore. We're like, okay, like what is the utility of this value? And utility here can mean anything.
Okay.
So if you're interested, exponential mechanism. The probability is more involved.
Yeah.
Part of the reason, kind of cover it. And then this is the accuracy of the exponential mechanism. And you prove this and make us homework assignment.
One thing you don't have to do.
I realized my 2 theory track lectures are like a hard sell for me because like class. That's all I've been doing.